Okay, good morning, everyone. The main mission for this class is just only one exercise. Okay, and at the beginning, I will make a short review of what corresponding of HH bar system. So today I used the representation. Here are some pieces and from the focus. Okay. Here are some pieces from Focus slide, and you can download the slide from the DZI website, right? Okay, and as mentioned, for HH bar system, there are 6 pairs, and which are classified by the different GPC quantum number and listed here. And because for each H corresponds to D or D star, and for each D or D star, the light degree of freedom, both of them are have 2 here, right? Have 2. So there are only 2 independent terms for the interaction, and denoted at because one half can couple to 0 or 1. So there are only 2 independent terms. One is called F0, and here. One is called F0 and one is called F1 for each SOS bin. Okay, so let me make it smaller. Okay, so in order to represent a specific HH bar system, there are 2 kinds of bases to represent. One is for use this basis to represent, and the other is use this basis. For convenience, I put these 2 bases here. Basis 1 and basis 2. For these 2 bases, it just corresponds 2 kind of couplings, 2 kind of couples actually. For basis 1, we couples the heavy quark spin and the other heavy quark spin together first, and the light degree of freedom of the first particle and the light degree of freedom of the second particle, and couples them to SL. Then we coupled the heavy quark part and the light part to the whole angular momentum. And for the basis 2, we just couple first. What we couple first is for the first particle's heavy part, and the light degree of freedom to the total spin of particle 1, and the same for the second particle. And then we coupled the J1 and J2 to the total angular momentum. And basically, these 2 bases can be related by the formulation listed here. Actually, this is just a basis transformation and a kind of combination of these 2 bases. So then here comes to our exercise is that because for different GPC quantum number, we can represent the, as mentioned, there are only two kind of free parameters, 2 kind of free parameters to represent the HH bar interaction. So the exercise here is just to derive the potential. Okay, to derive the potential, we can see that only CA and CB, 2 free parameters, and the CA and the CB just a kind of combination of the previous F0 and F1. Okay, so this is our exercise. So I will give you, for example, 5 minutes to think about this exercise. And I can give you a hint. It's just that you don't need to derive explicitly. You just need to make it clear how to derive. I mean the logic. You just need to make clear the logic. You don't need to calculate by yourself. For example, because there is a nice symbol, right? If you calculate by hand, it's very complicated. So later I will give you a note. Okay, I will give you a note to calculate this Niger symbol. You don't need to calculate by hand. You just need to derive how to derive the potential. Okay, just logic. I mean, you just need to make it logic clear. This is enough. Okay. Okay. You can think about that, and I think I'd better put the slide here because this is the key point. Okay, give 5 minutes to think about that. Then I will give you the answer. Maybe anybody know the logic of this exercise? Okay, it doesn't. Mm-hmm. Yeah, 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 yeah. Mm. Mm-hmm. Mm. Very good, very good. This is exactly the answer, the logic actually. Good. Okay, then, actually here is the mathematic. Okay, if you, I will talk about right now, and later if you are interested, I can send it to your email. Okay, because here I left answer didn't write. You can write it on yourself. Okay, so firstly, let's definite some useful things. The first thing is the Niger symbol. Okay, the Niger symbol is something like the matrix-like things, and I think I'd better for this one, Niger symbol. And then here is a decomposition. Decomposition is just to represent the basis two in terms of basis, in terms of to represent the basis one in terms of basis two, because the C1, CACB, or in other words F1, F0, and F1, they are both under the heavy quark spin basis. So what we want to do is basically just to represent the basis to another basis. So this decomposition just tell us this thing, okay, like under this formulation. Then as a basic example, let's focus on the first one, okay, 0 plus plus GPC. For the 0 plus plus GPC, we found that there are here. For 0 plus plus, there are two channels. One is DD bar and the other is D star D star bar. So it's a couple channel things. Mm-hmm. There are a couple channel things, and the potential here just represent the first one is the cross section of DD bar to DD bar, and the second one is the DD bar to D star bar, and the same as this one. And for the last diagonal element is basically for the D star bar to D star bar. Okay, this is the physical things, and then let's focus on, for example, this one, DD bar to DD bar. DD bar to DD bar, and the answer is CA. Now let's focus on how to derive this CA. The initial state is DD bar. Here I omit all of bar. Okay, DD means DD bar. Okay, D star means D star bar. Here I omit the bar. So the initial state is basically the DD bar. And for DD bar, if we want to represent this system by the basis 2, right? For the basis 2 is for D, SC equals to 1/2, SL1 equals to 1/2, and the total J for D is 0. And for D star, SC equals 1/2, SL equals to 1/2, and the total spin of the D star is 1. Okay, here we just focus on D. And so this is this meaning. For the first particle is D, so 1/2, 1/2, 0. And the second particle is also D, 1/2, 1/2, 0. And the total spin of the whole system is 0, because here we are focused on 0 plus plus. So this is why here is 0. Okay, this one. And for the final state is same with the initial state for D here and the D here, and the total spin is also 0. After decompose this system by the basis 2, then we can obtain the result. This is just to represent the initial and final state by the basis 1. Okay, and this is just for the first 3. Oh, here. For the first 3 number is corresponds to 1, 2, 3, and the second 3 number is 4, 5, 6, and the last number is basically the total spin of the whole system. And after that, we just need to make a cross-section of the initial state and the final state. And because here, it means this term need to multiply it by this term, and it's basically F0. One half times one half equals to 1/4. So here is 1/4 F0. And this term times this term is 3/4 F1. And after some simplification, then we can obtain the final result of this system. The potential is the Ca, and which is given in the exercise. Okay. So there's a question: why we don't have this term times this term? Why? Yeah, exactly. Very good, because they are octagonal, right? Okay. This is for one example for DD to DD. Then let's focus on DD to D star D star. Okay, it's the same. For the initial state, DD is basically same with the previous session, and for the final state, because here is D star D star, so here comes to for D star is 1/2 1/2 1. So here is 1/2 1/2 1 for the first D star, and the second D star is also 1/2 1/2 1, and the final spin of the whole system is 0. After decomposed, the same with before, and the final result is this one. Here we find that there is a minus sign of the answer given in the slide. Here it doesn't matter, because we can redefine the state by a minus sign. For example, we can define the two channel. Okay, one defined as A, and the other defined as B. There are two states. And for the potential is A to A and A to B, B to A and B to B. This is the potential. This is the corresponding potential for the first one. If we redefine the second state, for example, as A and minus B, just add a opposite sign to the state. It doesn't matter. Then this corresponds. Let's go to A full, minus A to B, and minus B to A, and B to B. Okay, we found that the diagonal element doesn't change. The only change for these two circumstances, just the off diagonal has an opposite sign. So the opposite sign just come from the redefinition of one of the state. So it doesn't matter. Does that make sense to you? Okay, good. Then actually everything is the same. So I won't expand these two. Okay, I just want to talk basically this one, because there are some different things. For 1 plus minus JPC DD star to DD star, and the given answer is CA minus CB. As mentioned, we can also decompose the initial state and the final state to this one. We can review again. Okay, for D, 1/2 1/2 0. For D star, 1/2 1/2 1. And the total spin right now is 1, because we are construct a JPC equals 1 plus minus. So here is 1, not 0. Okay. And for the final state, D equals to 1 1/2 1/2 0. Also, D star 1/2 1/2 1, and total spin is 0. After decomposition, these two state is basically represent for the basis 1 is like here. But actually, this state doesn't exist. This state doesn't exist. So here I rewrite the initial and the final state. Here I just represent the first two terms and omit the last term. Why we omit the last term? Because here, this one represent SCC bar, right? Do you remember both SCC bar and SL has two kind of quantum number, 0 minus plus or 1 minus minus, right? So this 1 here just corresponds to 1 minus minus. So two kind of minus minus, two kind of 1 minus minus, they cannot be 1 minus plus. Oh, sorry, 1 plus minus. Right? Because we are focused on S wave, the p parity is not conservative. So this is why this state cannot exist. Okay? Okay, okay. So here we throw away this state, and the same reason for this one. So the only two terms left for the initial and the final channel is is just the first two terms. So we need another overall overall factor to renormalize this state. Okay, so here I just write a square 2 here to make the state normalized. And then the others are same with the previous case. This is what I just want to say. Okay. Any question for this one? Okay. And for this case, I didn't write anything. If you are interested, you can copy this note and you can go back to your home or school and write by yourself to check if you really understand these things. Okay. Okay. For the others, for the 1 plus plus case, we can focus on here. Only one channel. 1 plus plus is this one. Okay. DD star, DD star bar, DD star. So it's DD star to DD star. Again, D, 1 plus 1 plus 0, D star, 1 plus 1 plus 1, D, and D star. And the total spin is again 1. After decomposition, look, here I also omit something. Here I omit these two. The same is the reason is same with here. Because 0 represents 0 minus plus, and the 1 is 1 minus minus. These two cannot couple to our 1 plus plus. Okay, so these two does not exist. These two also does not exist. Only these two. So the final result is basically CA plus C1, CA plus CB. Maybe you have question that even since the why these two state they are not exist? Why the CD coefficient or say Naizier symbol they are not 0? We know that this state cannot exist actually, right? Why the Naizier symbol are not 0? This is why. Yeah. Yeah, very good. This is exactly the answer. Okay. And the same circumstances also happened for the GPC equals 2 plus plus. And we found that for these two system 1 plus plus and 2 plus plus the potential is the same. So the final result is just here. Okay. Any question? No? Everybody understand? Really? Okay, so this is our last exercise actually. Then if oh. Oh, sorry. Okay. Okay.
For the fact that V is related to T. For example, through Lippmann-Schwinger equation at the first order, so I can write B in that way for this reason, or so. Why I can write the potential in that way?
Actually, this potential, it does not correspond to any basic potential. Okay, because we can focus on, we can understand this thing by effective theory. Any interaction or any amplitude, we always can expand this potential as a leading term, and in terms of momentum plus blah 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 blah, right? And what we derive is just this one. Yeah, and if we want a more higher order, for example, C1, C2, it's the same. Just the number is different. Just the exact number are different, but the relation of them are basically this one, because this is constrained by heavy quark spin symmetry. Okay, so we don't specify this is any kind of hadro strong interaction. It doesn't matter. We doesn't care about that, because no matter what it is, we can always expand the potential by terms of momentum. Okay, welcome. So maybe I can send this to your email, but I'm afraid I don't have your email. So if anybody wants this note, you can come here and put your email here, and I will group send it to you. Okay. And then, if no more question, I think we can stop here. Okay. Thank you. Thank you.